So we're going to talk about what a mineral is. We're going to talk about what mineral resources are. We're going to discuss the geological processes that make them. We're also going to talk about economics. We can't get past that fact. We just spent a great deal of time talking about energy, and I know I mentioned it several times that our first consideration has to be cost. What are the economics of that situation? We have to compare what it's going to cost us getting the fossil fuels out of the ground to what we can sell them. Same thing with minerals, ladies and gentlemen. That's our first consideration, is cost, is the economics of the situation. And then we're going to look at environmental impacts. And the good news is a lot of the environmental impacts from mining minerals are going to be the same as when we mine for coal. So we're going to see a lot of similarities there. And so let's begin by defining what a mineral is. A mineral is a natural compound that is composed of one or more elements. They are the basic building blocks of rocks. So elements make up minerals, minerals make up rocks. And we've already talked about rocks in this class. Now, in order to be considered a mineral, you have to have 4 characteristics. You are naturally occurring, which means that any synthetic gemstones, like cubic zirconium, are not considered minerals because they're man-made. 2, they're inorganic, which means they're not made by living organisms. 3, they have a specific chemical composition. I'm going to talk a little bit more about this here in a minute. And number 4, they have a crystalline structure. This is a very orderly arrangement of the atoms on an atomic level. Now I have 4 examples of minerals over here on the right. This bottom picture is quartz, perhaps the most common mineral in all of the Earth's crust. This is one of my favorites. This is wolfenite. This is garnet, a particular type of garnet used in jewelry. And this mineral you probably used this morning when you brushed your teeth. That is fluorite, where fluoride comes from, a major ingredient of toothpaste. Now let's talk a little bit more about that specific chemical composition, that third characteristic. Now here's what that means. No matter where the minerals are found, bottom of the ocean, top of the tallest mountain, they all are composed of the same elements. They have the same elemental composition. And I have an example here of halite. Those are a couple pictures of halite. Halite is sodium chloride. Okay, you might recognize that formula. That's where we get table salt from. No matter where halite forms, what environment it forms in, it's always composed of sodium and chlorine. If it's not sodium chlorine, it's not halite. So a specific chemical composition means that all minerals, no matter where they're found, have the same elemental composition. Let's talk about crystalline structure, the 4th characteristic. Now we're going to use halite again as an example, and what a crystalline structure is a systematic, orderly, 3-dimensional repeating pattern on how the atoms are arranged. So this is what halite looks like on an atomic level, with the gray balls being chlorine atoms and the red balls being sodium atoms. Now you'll notice this little black box here. Notice that this box repeats itself in this direction, in this direction, and in this direction. Now, that orderly, repeatable pattern gives halite its physical and chemical properties. Not all minerals have what this is called a cubic arrangement because they're composed into cubes. Different minerals will have different geometric arrangements which will affect their physical and chemical properties. Now, all of our minerals are divided into what are known as mineral groups based on what elements are in their structure. Now I have 7 groups listed here. This is by no means an exhaustive list. There are other groups than these, but these are probably the most common. We start with our silicates. Silicate minerals are composed of silicon and oxygen and are by far the most abundant mineral group in the Earth's crust. If we go back to that picture I just showed you of quartz, quartz is the most common mineral. Quartz is a silicate. We have native elements. These are minerals that are composed of one element. For example, we have gold, the element. We also have gold, the mineral. We have silver, the element. We also have silver, the mineral. These are native elements. A carbonate mineral has a carbonate group, which is a CO3 2- group in its structure. Oxides have oxygen in their structure. Hydroxides have an OH1- group. Sulfides have sulfur bonded to another element. And then we have our sulfates, which have a sulfate group, which is an SO4 2- group. So elements are classified based on, minerals are classified on their elemental composition. Now let me show you what some of these groups looks like. And let's start with our silicates. Okay. Once again, quartz is probably the most abundant mineral here of the most abundant mineral group. We have what are called micas. These are sheet-like minerals. An example here would be biotite. This is microcline, what is known as a feldspar. And biotite, microcline, and quartz are very common minerals in granite, a very common igneous rock. We also have a silicate group called pyroxenes. This is an example of diopside. And then this is olivine. If you remember earlier in the semester, we talked about the 3 layers of earth: core, mantle, and crust. Olivine is pretty much what the mantle is made up of. That's its composition. Our native elements. Here we have gold, silver, sulfur. And I always like to point out these examples. Graphite, which is pure carbon, which is what is used in pencil lead, and diamonds, which also is the same elemental composition, pure carbon. The differences between graphite and diamond is the crystalline structure. Diamonds have been squeezed and cooked at very, very high pressures and temperatures, and so the atomic arrangement, the crystalline structure, is completely different than graphite. Graphite you can get for a couple bucks. Diamonds you can get, depending on color and clarity, for maybe 10,000, 100,000. So same from an elemental standpoint, but different from a crystalline structure. Here are carbonate group. The 2 most common minerals here, calcite is probably the most common, and dolomite. These are very common ingredients of sedimentary rocks. We have smithsonite down here. This is an oxidized copper deposit. Malachite is the green mineral you see here. Azurite is the blue mineral. We also have rhodochrosite. If you've ever heard of this sweet mine Sweetwater mine, in Colorado, absolutely beautiful specimens of rhodochrosite, a carbonate mineral. Here's our oxides. This is corundum, otherwise known as ruby. This is an aluminum oxide mineral. We have magnetite, an iron oxide mineral. On the other hand, these are our hydroxides. We have goethite here, which is an iron oxide hydroxide mineral. And then we have limonite. This mineral you probably recognize by its more common term called rust. Rust, or limonite, is actually a mineral. It's a hydrated, which means it has water in its structure, iron oxide hydroxide. Here are sulfides. Remember that sulfur bonded with another element. We have pyrite, which is an iron sulfide. This is fool's gold. Remember, this is what creates acid mine drainage, ladies and gentlemen. You need water to react with pyrite in the presence of oxygen, and you get that colorful, acidic, heavy metal-rich water. Here's galena, a lead sulfide mineral. we have one of my favorite minerals, cinnabar, which is a mercury sulfide mineral. You do not want to lick cinnabar, very, very bad for you. And then sphalerite is a zinc sulfide mineral. Our last group are our sulfates. And we have probably the most common one here called gypsum, which is a hydrated sulfate. It has water in its structure. Gypsum is used for wallboard. So if you're looking at your wall right now, probably composed of gypsum. Anhydrite is the non-hydrated form. It's a calcium sulfate mineral. We have celestite, which is a strontium sulfate, and then barite, which is a barium sulfate mineral. Now, we talked about what a mineral is. Let's now define what a mineral resource is. If we have a natural concentration of useful elements, we're going to define this as a mineral resource. So if we have an enriched mineral deposit and those elements are useful to us, it's a mineral resource. Now, minerals, just like fossil fuels, are an absolutely essential part of our economy. We use minerals every day, from the salt that you put on your eggs this morning, to the fluoride that you brushed your teeth with, to all the minerals that go into making the laptops or your smartphones, or even minerals that go into the production of cars. Pretty much everything we use either requires minerals to make it or has minerals in it. Now, the availability of mineral resources is affected by a country's wealth. Remember, we've talked about GDP already. Remember, that's a measurement of wealth, gross domestic product. So generally, if we go back to our demographic stages, generally what we see is post-industrial countries have much better access to minerals than, say, a pre-industrial country. So it all goes back to economics here. The wealthier you are, the higher your GDP, the more access to minerals you have. Now, I wanted to give you an example of how much we're actually talking about here. And so in 2017, raw non-fuel minerals in the U.S. we mined were worth a little over $75 billion. So think about that. For 1 year, we dug out minerals out of the ground that were worth $75 billion. We then took those $75 billion worth of raw minerals and we made processed products from it. So laptops, cars, whatever, that were worth almost $3 trillion. And I want to stop and I just want you to let that sink in, ladies and gentlemen. We mined $75 billion. We took those $75 billion, we made processed products that we sold for almost $3 trillion. That was about 15% of our GDP for that one single year. Minerals, absolutely essential, even though we generally don't think about them, or at least consciously think about them. Now here, what this is value of non-fuel minerals produced. This is 2016 by state. And look who's in the lead. Nevada is. Okay? Nevada in 2016 produced a little more than $7.5 billion worth of minerals. Followed by Arizona, about maybe 5.75, and then Texas, a little under $7 billion. California's here, Minnesota is here, Florida, and Alaska. These are the states that produce the most raw minerals. Now, when we talk about mineral resources, there's two types. There are metals and there are non-metals. Now, metals are broken into two other groups, actually three other groups. We can have ferrous metals, which are metals that are enriched in iron. Ferrous comes from the Latin word ferric, meaning iron-bearing. We also have non-ferrous metals. These are metals that don't have any iron in them. We also have precious metals. Now, precious metals are metals that are rare but extremely useful. And they're useful because they have a trait called malleability, which means they can be bent and molded into a lot of different geometric shapes, making them particularly useful in jewelry. So precious metals, rare but extremely useful. Examples would be gold, silver, platinum, are all classified as precious metals. Now, those make up a minority of our use. 90% of our use are non-metals, and examples would include building materials. Think of the sand and gravel that goes into construction or even just making concrete. There's a group of minerals called clay minerals that are important in the construction of ceramics, and then decorative rocks. I like to think of Las Vegas as the capital of decorative rocks. Go into any casino, go into the bathroom and see the different types of rocks that the countertops are made of, or the flooring is made of. We also have industrial uses. These would be minerals that are used in industrial processes. We also, especially in the U.S., because a major export, what we sell on the open market are agricultural goods, we also use mineral resources in agricultural uses. The biggest one there is phosphate. That is a main ingredient in most fertilizers. Now, here are our metals. So I give you examples again. Here's gold, copper, which is very useful, particularly in electrical wiring, silver, and this is a very unique and rare mineral where titanium comes from. Here's our nonmetals. Here's that phosphate. I know it doesn't look like much, but very, very important ingredient in fertilizers. This is a halite mine up in Canada. That's not cocaine, ladies and gentlemen. That's salt right there, major salt deposit. And then sand and gravel quarries. We actually have several of these around Las Vegas where you will see them taking both sand and then coarser particles called gravel out of the ground. Now, if we look at this on a per capita or per person basis, these are some of the most common minerals, and I want to draw a line right here. Everything above this line would be non-metal mineral resources. Everything below the line are metal mineral resources. So if you look at some of our biggest uses, crushed stone for construction, once again sand and gravel, salt, God knows we put salt on everything. Here's that gypsum, once again a major ingredient in wallboard, phosphate for our agricultural uses, and then potash. This is where gunpowder comes from. Okay, think about it. In this country, we love our McDonald's and guns. There we go. Down below here are all the metals. Iron is the biggest use, followed by aluminum, copper, zinc, and then lead. Now, just like our fossil fuels, we don't see a even distribution of minerals across the Earth's surface. They are controlled by geologic processes which don't operate everywhere. So we're going to see, just like we saw with fossil fuels, there's going to be winners and losers. Okay? Think about it. You think of oil, what do you typically think of as winner? The Middle East. Okay? Maybe Venezuela in South America and parts of Africa. Same thing with minerals. Now, today, the demand for minerals is rising, and this hopefully will make logical sense. First, because of the exponential increase in human population that we've already talked about. More people demand more minerals. It's as simple as that, ladies and gentlemen. And we're also seeing an increase in wealth of our industrial countries. Remember we talked about, once again, the demographic stages, pre-industrial, transitional, industrial, and post-industrial. Well, look at the three countries that are currently entrenched in their industrial revolution now. China, India, and Mexico. Think about all three of those countries have major population densities, a lot of people, and as their GDP increases, their access to minerals increases. Their demand for minerals increases. But remember on the other side, minerals, just like fossil fuels, are non-renewable natural resources. Okay? We don't make them. Remember, they're made through geologic processes. So just like oil, coal, and natural gas, we don't have an unlimited supply of gold. We don't have an unlimited supply of silver. we have a very finite quantity on Earth. Now this is why, I don't know if you've heard of this lately, there are actually some companies that are actually trying to go out in the solar system, catch asteroids or meteors, bring them back to Earth, and actually mine those extraterrestrial bodies for their mineral content. As of right now, I don't know of a company that can actually do this, but this is what we're working towards. We know Earth has a finite amount of minerals, and so if we want more gold, silver, and other metals, we're going to have to go mine it in the solar system. Now, here's a picture of where the minerals are, and I want to point out 3 countries that have fairly large deposits. Probably the number one, the one you don't think about, is Australia. Okay, you can see a list of all the different elements they have, very enriched. China also has fairly large mineral deposits, as does South Africa. Think about their diamond industry. So those are probably the top 3 countries with the most minerals. Africa really doesn't have a lot, although they are discovering new mineral deposits in Central and North Africa. Middle East has very little. We do have some here in the US, and Canada does have some. South America has some fairly large deposits as well. But once again, it's an uneven distribution. Now, we don't want a mineral resource. We want something called an ore. This is when a mineral resource has become enriched enough or concentrated enough to be economical. Remember, ladies and gentlemen, just like with oil, we discover a new oil deposit. Do we instantly drill for it? No, we do the math. How much is it going to cost to extract versus how much can I sell it for on the open market? The same thing with minerals, guys. They have to be economic. We have to make a profit from what we have to pay to extract versus what we can sell on the open market. Now, in order to calculate whether a mineral resource is an ore, we calculate something called the concentration factor. This is the concentration of the given mineral in an ore expressed as a percentage divided by the average concentration of that mineral in the Earth's crust, also expressed as a percentage. So let's say that we find an ore body that's 30% aluminum. That's that first number there. So that ore body, that would be 30. We would then need to know what aluminum, the concentration of aluminum is in the Earth's crust to calculate the concentration factor. Now think of these concentration factors as there's, for every single mineral, there's a bare minimum. There's a threshold where below it doesn't make economic sense. Above, we can make money off of it. Now this depends, once again, on how abundant or rare that mineral is in the Earth's crust. So for example, aluminum and iron are so common in the Earth's crust that they can be profitably mined at a concentration factor between 4 and 5. So 4, boom, we can make money on an aluminum deposit. Now would we want that number to be higher? Sure. Okay, we'll mine a deposit of 4, but we'd like it if it was 50 or maybe 200, because the higher the concentration factor, the richer the ore, the more money we can make. Now mercury, on the other hand, is so rare in the Earth's crust, thank God, very, very toxic to us, that it needs a concentration factor of 25,000 to be profitably mined. So think of these concentration factors as a minimum threshold. And for every single mineral, we know the threshold. Below, it just doesn't make economic sense. Above, it does. Now, because the concentration factor depends on how abundant or rare a mineral is in the Earth's crust, we need to know the most abundant elements in the Earth's crust. Because if these minerals have these elements in them, they're going to be more common and are going to require a lower concentration factor to be profitably mined. Now here's the good news. 98% of the Earth's crust is composed of 8 elements, and I have them listed there on the right-hand side in decreasing order. So oxygen is the most abundant element. Magnesium is the 8th most abundant element in the Earth's crust. Here's why this is important. Let's say that we have a mineral that has sodium and iron in it, 2 of the most abundant 8. That means that it's going to be much more common in the Earth's crust and is going to require a lower concentration factor to be profitably mined. Now, I do expect you to memorize this list in order of the 8 most abundant elements in the Earth's crust, but I have a great mnemonic device for you, ladies and gentlemen. Okay, you ready? Only silly asses in college study past midnight. The only stands for oxygen, the silly for silicon, the asses for aluminum, the in for iron, college for calcium, study for sodium, pass for potassium, and midnight for magnesium, not manganese, magnesium. Now, I learned that mnemonic device probably while a lot of you were still in diapers, and it has really stuck with me. So it's a pretty good mnemonic device, just like the mnemonic device for the 7 kingdoms. Remember we talked about keep plates clean or family gets sick? This is a pretty good mnemonic device, guys. Only silly asses in college study past midnight. The 8 most abundant elements in the Earth's crust. Now, we've talked about minerals. There's a finite quantity. So there are 5 ways that we can respond to the limited availability of minerals. Number 1, we're running out of something, we go find more. And there are companies that hire geologists that know what environments are going to produce what mineral resources. And so they go looking for it. They go exploring for it. 2, you find a substitute. Back in the 20s, soda cans, actually 20s and 30s, soda cans were composed of tin. Now, we realized fairly early on that tin was a scarce metal. And so I think somewhere in the mid to late 30s, we switched to aluminum. And now soda cans are composed of aluminum because aluminum is a lot more abundant than tin was. 3, we can conserve and increase efficiency. Remember, conservation, a fundamental principle of this class, guys. To conserve means to save, to set something aside so that it's there for future generations. Now, we've been talking this whole semester. Do we do conservation well? We don't, okay? Remember, we're a consumer-driven society. We're taught to consume at a young age, not conserve. However, we do tend to increase efficiency. By increasing efficiency, we use less of a mineral resource to make something. That affects our bottom line. So it does behoove us to increase efficiency because we can save money. But conservation, we really don't do that well. We can recycle. Now, we've talked about this when we talked about waste, guys. And remember, we talked about the barriers of recycling. One of them was cost. Okay? The amount of recycling of a product is determined by the market. Now, think about this. Minerals with a high price, think of gold. Think of all these cash for gold places that have popped up over the last 10, 15 years. Think about it, ladies. You have a gold chain that breaks. Do you throw it in the trash? Of course you don't. You take it to a pawn shop, you take it to one of these places, and you get money for it. So precious metals, gold, silver, platinum, the market is going to say that the recycling rate is going to be high. Even think about copper. Think about when we had all these foreclosures, people were breaking into these empty homes and stripping the copper wires because they could get money from a scrapyard for the copper. Other metals like iron, there's really not you can't get any money for it. So the recycling rate of that is going to be very low. So we have the same barriers we did when we talked about recycling in general. Now, if you can't find more, if you can't find a substitute, if you can't conserve and increase efficiency, and if you can't recycle, our last option is you simply do without. Or, as I say, there are these companies that are working towards actually mining asteroids or meteors in the solar system. So I think that's where the future is heading. The problem is the cost is going to be very high. Think about it. You'd have to send a space, some kind of ship out into the solar system, find some way to snag a chunk of rock and haul it back to the Earth. That's mucho dinero, ladies and gentlemen. And so right now, not cost effective, but I think this is where we're heading. All right, now I mentioned earlier that mineral resources were created by geologic processes. Let's take a look at the 4 major geologic processes that create mineral resources. Now the good news is 3 of these we've actually already discussed in this class. That's the 3 types of rocks: igneous, metamorphic, and sedimentary. Think about it, ladies and gentlemen. An igneous rock is composed of igneous minerals. A metamorphic rock is composed of metamorphic minerals. A sedimentary rock is composed of sedimentary minerals. So those are going to be the same. The one that we haven't talked about is hydrothermal minerals. Now, what a hydrothermal mineral is, we have hot fluid. Generally it's water, but not always. Okay? So we'll say hot fluids, but mostly it's hot water. So you have a magma body in the surface, in the subsurface, gives off heat. This heats the water in the surrounding rocks, creating these hot fluids. The hot fluids then move throughout the rocks, chemically and physically altering them to produce brand new hydrothermal minerals. Igneous minerals are created from an igneous rock. And how did we create an igneous rock? We took a magma body, either at the surface or below the surface, and we cooled it. And so crystals will pop out of that magma body and settle to the bottom of the magma chamber. We have metamorphic minerals. These are minerals that physically and chemically change in response to jacking up pressure and temperature. And then sedimentary origin, we're going to talk about the 2 types here in a couple minutes, our evaporate and our placer deposits. These are either created by physical processes or created by chemical processes. Now, we took a look at sedimentary rocks. Remember, they were created when bits and pieces of rock were cemented together. That would be physical processes. We also had sedimentary rocks that were created by either biological activity or chemical processes. That would also create these chemical sedimentary minerals, generally caused by precipitation reactions. So you have a saturated solution somewhere, you add a little bit more, and those minerals precipitate out, or they change from an aqueous phase, a dissolved phase, back into the solid phase. Now let's take a look at all 4 of these, and let's start with our hydrothermal minerals. So once again, the first thing we need are hot fluids. Where do we get those hot fluids? Well, the most common setting is an oceanic divergent plate boundary. Remember, we've talked about this before, guys. So in the middle of our oceans, this plate is moving this way, this plate is moving this way. Magma upwells from the mantle, and we actually create new crustal material. Well, this magma is also going to heat the seawater that's present in these rocks. And so that hot fluid then is going to circulate in these areas, physically and chemically changing the existing minerals into hydrothermal minerals. Okay? Now this is the most common location. We can also get hydrothermal minerals at the Earth's surface associated with either geyser or hot spring activity. This is a picture of Yellowstone. You'll notice the kind of yellow and orange rimming the geyser. Those are hydrothermal minerals created by the action of the hot water rising to the Earth's surface. So the most common is an oceanic divergent plate boundary, but If we get a magma body rising close to the surface where we create geyser and hot spring activity, we'll also see hydrothermal minerals as well. Now, I wanted to take a little bit deeper dive into that oceanic divergent plate boundary. In this environment, we typically see what are called hydrothermal vents. These are cracks in the crust where heated water escapes from the subsurface. And I'm sure you've seen pictures of these. These are called smokers. We have black smokers. These are minerals enriched in iron and magnesium. And we have white smokers. These are typically enriched in sodium and calcium. And so what these are is it's not actually smoke. What's happening is that hot fluid is rushing out. It's hitting the cold ocean water, and boom, the minerals are precipitating out of that hot solution. So it actually looks like smoke. It's not smoke, it's these precipitation reactions. And so these are going to be common around our oceanic divergent plate boundaries. They're also found around volcanically active areas, including subduction zones and hotspots. So we can find these hydrothermal vents. Most common is an oceanic divergent, but we can also find them at subduction zones. Remember, that was a convergent plate boundary, and hotspots, where you get this plume of magma rising to the Earth's surface. Let's talk about our igneous minerals next. And so let's picture that we have a magma body in the subsurface, and over time it's slowly cooling. Well, as it cools, it's going to reach certain temperatures where different minerals are going to come out of solution. So let's take a look at an example here. Let's say that we're cooling this magma body and we hit the first important temperature here, where magma A, the green mineral, precipitates out of solution and slowly settles to the bottom of the magma floor. We continue to cool that magma body. It hits a second temperature where a brand new mineral with a different elemental composition, the brown one, precipitates out and sinks to the bottom of the magma chamber. We continue to cool it. We hit another temperature where now the white mineral with a different mineral composition precipitates out and sinks to the magma floor. And so often what we'll see are these igneous deposits have a layered structure, where one layer will be enriched in one mineral, the other layer will be enriched in a brand new mineral. Now, what minerals precipitate out at what temperature is defined in geology by something called the Bowen's reaction series. So this tells us exactly what minerals will precipitate out. So here we have the high temperatures are up here. So olivine is one of the first minerals that will precipitate out. Then we'll get our pyroxenes, our amphiboles. These are all silicate minerals. And then our biotite, our micas. So on this side, these are all the silicate minerals that precipitate out. On this side, we then have different minerals. Calcium-rich minerals actually precipitate out at a higher temperature. Sodium-rich precipitate out at a lower temperature. But if we know the elemental composition, we can predict when it will precipitate out of that cooling magma body. Now here's an example. These gray layers that you see right here, this is the igneous mineral called chromite. It's an iron oxide mineral. And so you can see these layers enriched in chromite, so formed from a cooling magma body. Our metamorphic minerals are produced through metamorphism. Now this is the mineralogical, chemical, and textural changes to pre-existing minerals that occur in a solid state. Now textural generally means size. So often you can create a mineral that has one appearance to it and create another mineral that has a brand new appearance. So that's what we mean when we say texture. How does the mineral look? So we can change the mineralogical composition, the chemical composition, or the textural appearance Now, the important thing is that it occurs in a solid state. Whenever we melt rock, we're no longer dealing with metamorphism. We're dealing with magma, which would then generate igneous rocks. So it's important to note, and I think I talked about this when we talked about the 3 types of rocks, that if you increase pressure and temperature just a little bit, you'll have what is called a low-grade metamorphic rock. Well, low-grade metamorphic rocks have low-grade metamorphic minerals, minerals that change just a little bit. We then have medium grade, and then we have high grade. These would be minerals that change a lot. Now, this line right here, this is the point of melting. So any point past this, we generate magma, and we're not talking about metamorphic rocks anymore. Now, if we talk about a place where metamorphic minerals are going to be fairly common, this would be at a convergent plate boundary where we create a subduction zone. So once again, we have these 2 plates colliding. The denser plate gets shoved underneath the less dense plate. Remember, we called this the subduction zone. Well, as this plate dives back into the mantle, pressure and temperature increase. Here at shallow depth, we would have what would be considered low-grade metamorphic minerals. Medium depths would produce medium grade. The deeper it is, the higher the grade it is. Now, eventually that rock melts, we generate magma, and this results in igneous rocks. So we can actually find the different types, low grade, medium grade, or high grade, as the subducting slab gets pushed underneath the other plate. Now, this is an example of gneiss. I showed you a picture of this. This is a very high grade metamorphic rock, so high grade that you can see that the individual minerals have alternating layers. There's a layer of white minerals, then a layer of dark. Light, dark, light, dark, light, dark. Incredibly high pressures and temperatures to generate that type of rock and those minerals. Here's our sedimentary minerals. And once again, can be formed from either physical processes, that would be placer minerals, or chemical processes, that would be evaporate minerals. Now let's take a look at the difference. Now, a placer mineral, this is an accumulation usually of precious metals, gold, silver, that are formed when gravity washes minerals downslope into streams. So picture this. We have a certain type of igneous rock that has little flecks of gold in it. Over time, a river flows across that igneous rock and plucks the little gold pieces through erosion. It then transports it in the stream channel, and eventually then it will deposit it as it loses energy. Remember, actually we're going to talk about this more when we get to water resources and talk about streams, which is our next topic. These are called placer deposits. If you've ever seen those old pictures of old miners panning for gold in streams, that's what they're looking for. Little pieces of silver and gold that were actually made at point A. The river picked them up and moved them to point B. Evaporate deposits, what we need is a shallow body of seawater. What happens is the water evaporates off, and what's left behind is enriched in evaporate minerals, halite, gypsum, and hydrite. And so we'll actually form these mineral deposits, these evaporate minerals, on the bottom of these kind of isolated shallow seawater bodies. Here's what these look like, and you can probably see this is a very famous picture taken of the kind of the salt deposits that very commonly occur in New Mexico, Arizona, even here into Nevada. Now, let's talk about the environmental impacts. And as I said before, a lot of what we're going to talk about, we've already talked about in fossil fuels. So it doesn't matter whether we're mining for coal or mining for, let's say, pyrite, the impacts are going to be very, very similar. The first one is this visual blight, created when we extract the minerals from a surface excavation. We've talked about this, okay, guys? Visual blights are created by coal mines, also by mineral mines. Now, I want to point out something. A very, very important distinction in vocabulary here. A surface mine for coal was called a strip mine, correct? If we have a surface excavation for any mineral, we call it an open pit mine. So if I use the term strip mine, I am solely talking about a surface excavation for coal. If I use the term open pit mine, I'm solely talking about a surface excavation for minerals. Now, we also create a generation of huge amounts of waste. Let me go back to an example I used earlier. Let's say that we find an ore body that's 30% aluminum. So the aluminum is what we want. Well, what's the other 70%? It's waste, ladies and gentlemen, that we have to properly dispose of. We also have contamination issues as well, particularly when it comes to heavy metal contamination. So acid mine drainage, or AMD, is a problem with coal mines. It's going to be a problem with a lot of our heavy metal mines. Instead of the acid mine drainage being a consequence of water getting in the coal piles, now we might be mining cadmium or mercury that's going to create that acidic, heavy metal rich water. We can also create greenhouse gases from something called smelting. That's when we melt metals down. So if you've ever seen like a gold bar, you guys realize that that's not how it forms in nature. What we'll do is we'll take all these little bits and pieces of gold from mining, we'll smelt them down, and we'll pour the liquid gold into a mold, which creates then that solid gold bar. When we do that, when we melt metals in order to put them into different shapes, we will create greenhouse gases like carbon dioxide, methane, which results in the greenhouse effect and then global warming. And then we also have subsidence from underground mining. Underground mine collapses, causes all the rocks on top of it to either gradually or suddenly sink or settle. Now, I want you to take a look at this list, and I want you to think if we talked about this when we talked about coal. Visual blight. Yep, we've already talked about it. Generation of huge amounts of waste. Yep. Contamination issues. Yep. Greenhouse gases from the burning of fossil fuels. Yep. And subsidence. Yes, that's not a new list, ladies and gentlemen. So it really doesn't matter whether we're mining for coal or minerals. We generally produce the same environmental impacts. Now here's this visual blight. This is a very famous or infamous, this is the Bingham Canyon open pit mine. This was a big copper excavation up in Utah. And once again, if you look at that, it's an eyesore. That's what we mean when we use the term visual blight. It's ugly. Mining waste. Now, I wanted to give you an example. Currently, there's about 1,200 active hard rock mining sites in the U.S. The majority of those are for copper and gold. Now, those 1,200 sites generate about 1.5 billion tons of waste every year. Now, coal mining produced hundreds of millions of tons of waste. Mineral mining actually produces a couple billion tons. So believe it or not, open pits generate much more waste than strip mines. Now, some of it is solid waste. The majority is solid waste, but we also have liquid waste as well. Now, I wanted to give you an example here. So in order to produce 1 ton of pure aluminum, we need to mine or extract 4 to 5 tons of a mineral called bauxite, which is an aluminum oxide mineral. So 1 ton of pure aluminum requires 4 to 5 tons of bauxite. That 4 to 5 tons of bauxite produces 13 tons of waste, 10 tons of solid waste, and 3 tons of a kind of slurry, muddy, red, muddy toxic waste. So 1 ton of aluminum equals 13 tons of waste. Now that's aluminum. A lot of the precious metals, it's even worse. If you look at gold, for instance, I've seen numbers as high as 1 ton of gold produces anywhere between 25 and 30 tons of waste. Now, when we talk about waste, we need to talk about something called tailings. Tailings is a fancy word that is the uneconomic waste portion that's left over when we separate the ore from what we don't want. So remember that we need that ore to be economical. So once again, we take that 30% ore body, we extract the 30% we want, the 70% we don't, that's tailings. Okay, it's the uneconomic portion that's left over. Now, in a lot of cases, particularly for precious metals, you'll actually store the liquid waste on site in what is known as tailing ponds. Now, these two pictures here are of a mining site up in Montana for platinum. Now, I know you look at that water and go, I would love to swim in that. Believe me, ladies and gentlemen, no, you do not. That is AMD. That's that very acidic, heavy metal rich, very, very toxic waste. And this is how we produce it. Let me give you an example of gold. So let's say that we found little stray pieces of gold in a particular igneous rock. We mine the entire igneous rock. We grind the rock down into dust, and we spray a liquid cyanide over the rock. What happens is the cyanide dissolves the gold. So we collect the cyanide and the liquid gold. We separate the gold, what we want, but now we still have liquid cyanide left over. That would be tailings, and we would store that liquid cyanide in these tailing ponds. And so you'll notice, in this case, we have a tailing pond, and look at the color. You see yellows, reds, and oranges. We know we have a lot of heavy metals in these tailing ponds, which results in, if it escapes off-site, in this acid mine drainage. You can actually see water leaking out of an underground mine that has been contaminated. In this case, we've contaminated this river. Water is usually not yellow, no matter how much you pee in it, ladies and gentlemen. And then I think yellow is cadmium. I think so that yellow coloration indicates the heavy metal cadmium. In this case, you'll actually see yellows, oranges, and reds. I know the red is mercury. I'm not sure what the orange is, but I know it's very, very toxic heavy metals. Remember, our bodies can't metabolize those, and so they build up, they bioaccumulate. Here's subsidence. These two pictures were taken in Russia. This was a potash mine, underground mine that collapsed and created something known as a sinkhole. We'll actually talk about sinkholes in our next topic when we talk about water resources. Here was an underground gold and copper mine in Australia where we had subsidence. So the mine collapsed, which caused the material on top, in this case, to suddenly sink down. Now, as we've done before, what can we do to minimize the environmental impacts? We're never going to eliminate them, but what can we do to lessen the environmental impacts? Well, the first thing we can do is we can use impermeable liners in tailing ponds. So if we have a tailing pond on site, before we put any liquid tailings into it, we're going to line it. Usually with impermeable material, maybe plastic liners, maybe both. So that material doesn't leach into the subsurface, creating contamination. Once our mining operations are done, we're going to have to treat all, not only contaminated water in the tailing ponds, but all solid waste is either going to have to be shipped off site or is going to be treated on site. Filling in underground mines with waste rock to reduce the risk of subsidence later on. Monitoring air and water quality. This is very common. If you have an active mine, every 3 months or so, you'll take air samples and groundwater samples. You'll you also might even sample if there's any surface water in the vicinity to ensure that nothing from the mines is escaping, because you are legally and financially responsible for any cleanup. So if something does leak, you want to catch it early. And then we use air scrubbers. So for that smelting operations, we've talked about what air scrubbers are. It's a generic term for any device that removes the fine particulate matter or removes some greenhouse gases before the exhaust goes up a chimney into the atmosphere. We also have reclamation is very important. We talked about reclamation of coal mining sites. We were going to have to reclaim our open pit mines just as well. Remember what that involved. We'd take all the waste rock, we'd fill in the open pit, we'd recontour to match what it looked like before, we would plant native vegetation, and then treat waste. Remember the purpose of reclamation, ladies and gentlemen. It's to restore the land to its pre-mining condition so that you couldn't tell there was a mine there to begin with. Now, there's a lot of things that we can do. Some open pits have actually been turned into recreational lakes after mining operations. That would be okay for like if it was a sand and gravel open pit mine, but obviously you couldn't do that if you were mining for mercury, because the water would have some traces of mercury in it. You can replant it and make it into parks. We talked about an old coal mine in Indiana that was turned into a municipal park. Once again, you have to make sure, though, that the soil had no lingering traces of contamination. And there's another kind of unique idea that's been invented, I'd say the last 20 or 30 years, where you make what is called a constructed wetlands. And I'll show you an example of this. But what you do is you fill in the open pit, you fill it with water, and you plant certain water-loving species of plants. And what happens is the plants absorb and filter any lingering traces of contamination. So instead of you taking all the contaminated soil or all the contaminated water off site, you let nature clean up your mess for you. Now in 2011, about 50% of the land that had been used by the mining industry had been reclaimed. You have to remember, most of your reclamation laws weren't passed until the 70s or 80s. Remember, 70s was the golden age of environmental legislation. So if you were you had an old open pit mine back in the 40s, 50s, and 60s, you didn't have to reclaim the land, and you didn't because it costs money. Reclamation costs money. And so you can think of that depending on your philosophical bent. Are you a person whose glass is half empty? Then you're like, well, crap, only half has been reclaimed. Or are you a glass half full where you're like, well, that's good, at least half of the land has actually been restored. Now, just like we were talking about in our coal mining, I wanted to share with you 3 examples of reclamation projects. So this first picture, and remember, think of these as kind of plastic surgery photos. Here's the before picture. This was the Flambeau lead zinc sulfide mine. A very, very rural area. Nowhere near any of the major towns in Wisconsin. But here's what it looked like before. They decided to make one of these constructed wetlands. So they filled it in, they planted these certain species of plants that could absorb lead and zinc heavy metals and still be okay. Now notice, if you take a look at this after picture, can you tell that there was even a mine there to begin with? No, no, no. That's the purpose of reclamation, ladies and gentlemen. Here's one of my favorite projects. This was in Golden, Colorado. This was an old limestone and clay open pit mine. And you can actually see the sidewalls here of this mine. So instead of filling it in, they actually built. Somebody had the foresight to say, well, let's not fill it in. Let's make an award-winning golf course. And I have actually played on this golf course. It's absolutely spectacular. Expensive, but spectacular, ladies and gentlemen. So a creative way. And I thought I'd share an example with you a little closer to home. This is a reclamation project in McGill, Nevada, up in northern Nevada. Here's the before picture. The Nevada Consolidated Copper Company had about 4,000 acres of tailing storage. I know this might look like soil to you. Those are tailings. That's solid waste. They came in, took them about 4 years to complete the project, but they turned it into a prairie, into a grassland. Once again, you look at the after picture and you couldn't tell that there was a mine there to begin with. That's the purpose of reclamation, ladies and gentlemen. And that is the end of our discussion of mineral resources.